All right, so this week we are looking at climate models. And we've already encountered climate models a little bit in some of our past lessons. We've looked at some of the outputs of climate models. You've played around with some very simple climate models in your exercises. But we want to take some time to really dig into how do climate models work, because they're so essential for understanding climate change, because we can't simply put a bunch of Earths in a laboratory and do things to them to see what happens. We have to be able to model the Earth system and use that to explore the possible ramifications of different things that might happen on our Earth. So our goals for this lesson are first to understand what climate models can and can't tell us, right? What kind of information can we get from these models? And then how to use some basic climate models to examine the Earth's climate system. So let's start off by asking, what is a model? We can think of a model as a mathematical representation of the processes making up the climate system. So we've got all of these processes happening out there in the world, and if we create a set of mathematical equations that describe those processes, and then we can feed different data into those equations and see what results come out of it, then we've made a model of the system. And I always like to lead off this lesson with this quote from George E.P. Box. He said, "All models are wrong, but some are useful." Anytime you're making a model of a system, your model is not going to be exactly the same as that system. Right? Your model is going to simplify that system. It's going to focus on certain aspects of that system and leave others out. And it has to do that. That's what makes a model useful, is that it simplifies things. So it's easier to run the model and see the outputs. It's easier to understand what the model is doing as compared to the real world that is just so big and so complicated. So the simplification that goes on in creating a model is the point of the model, just like a simplification of making a map. And a map doesn't include everything that's actually there on the Earth, but simplifying it makes that map useful to us. So our criterion for a model should really be, is this model useful? Does the output of this model help us to make decisions, like decisions about whether or not to adopt a certain policy at the national or international level, or decisions about what kind of car to buy? Right? There's a variety of decisions that we might be trying to make, and models can be useful in helping us make those decisions, even though the model is not exactly the same as the thing that it's modeling. And when we look at models, one good way to kind of distinguish different sorts of models is to look at these three features that I've listed in the third bullet point there. We can look at the spatial scale and resolution of the model, the temporal scale and resolution, and the set of variables and parameters that are in it. So the spatial scale and resolution, right? Spatial means having to do with geographical space. So how big of an area is this model covering? Is this a global model that's trying to model the entire Earth? Or is this a regional model that's just looking at one part of the Earth? And resolution means, how detailed is that model? Is it describing what's happening, from 1 square meter to the next, or is it kind of lumping things together into big, several kilometer sized chunks? Because the more detail you get, obviously that can tell you about finer scale processes, but it also makes the model way more complicated to run. And then temporal scale and resolution, the same thing, having to do with time. So what time frame are we looking at? Are we trying to model just the next 100 years? Are we trying to model, millennia? And how detailed are we chopping that up? Are we looking at day by day by day changes, or are we looking at, year to year changes? And then the set of variables and parameters. What kinds of things go into our model? You should be able to see from all the stuff we've done in our previous lessons how many different aspects of the Earth have connections with the climate system. So which of those aspects of the Earth are we going to include in the model as either a variable, something that can change as part of the model, or as a parameter, something that does not change. It's like a fixed thing. So for example, there are interactions between plate tectonics and climate change. that the volcanic activity that comes from plate tectonics and the movement of sediments into the interior of the Earth through subduction, those all affect the climate system. But those are things that happen so slowly that if you are designing a climate model to predict what's going to happen in the next 100 years, it just makes your model complex for no reason to try to model those tiny changes that would come about from plate tectonics. So it's easier to just leave that out of the model. On the other hand, if you're trying to build a model that will tell us about climate changes over the course of 100 million years, then you're going to need to include those plate tectonics things. Because at the scale of 100 million years, plate tectonics does make an appreciable difference, and you'll get inaccurate results if you don't incorporate that. So which variables and parameters you include in the model will distinguish different sorts of models. So we conventionally divide climate models into 3 types of different levels of complexity. So we can start with the least complex type of model, which is called an energy balance model. And an energy balance model is basically calculating energy going in, energy coming out, and temperature for the Earth. And so the simplest energy balance model is one that we saw a few weeks ago, the Stefan-Boltzmann equation, right? All we needed to know was the amount of energy coming in from the sun, the albedo, the temperature of the Earth. That could solve that equation. The models that you've used in some of your recent homework assignments, your lab activities, have also been energy balance models. They're very simple models. They're mostly looking at energy coming in and going out from the Earth. Then we can move up a stage in complexity. We get what are called Earth models of intermediate complexity. So a pretty self-explanatory name for this class of models. And what these EMICs do is they incorporate space and time. So if you think back to those energy balance models we've used, they've treated the Earth as a single thing, right? The Earth is a single unit with a single amount of energy coming in, going out, a single average global temperature. If we want to distinguish different parts of the Earth, if we want to be able to look at processes that are happening differently in different parts of the Earth, then we'd need to use an EMIC. We'd need a model that can incorporate the fact that we have different places around our Earth. And likewise with time, that Stefan-Boltzmann equation, that gives us the sort of final outcome when everything has stabilized. But we know things don't stabilize instantaneously. It takes some time. For example, if we get additional energy coming in, it takes some time for the temperature to reach equilibrium with that. And so if we want to be able to track what happens over time, we also need a more complex model, and that gets us into this EMIC territory. And so some of the more simple EMICs are also able to be run just in your web browser. And so we'll be looking at one of those in our activity for this week. But the more complex you get, the more computational power you need to run your climate models. And so when we get to the most complex class of models that are called general circulation models, or GCMs, those are so complex, you can't just run that in your browser. You need supercomputers using dedicated time to do these model runs. It becomes a big undertaking because the models are so complex. And so you see the picture there is a representation, sort of a simplified representation of what goes into a GCM. And so you can see we've got this grid horizontally and vertically for the atmosphere, for the ocean. We're factoring in things like sea ice and ice sheets on land, the exchange of heat and CO2 with the soil and with vegetation to the atmosphere. We've got a lot of different processes that are being built in here, and we're looking at how those change over space, right? On ocean areas versus vegetated areas versus bare soil areas versus ice areas that you can see on that little diagram. So I had mentioned spatial resolution as being an important element to distinguishing different types of models. And so most climate models that are complex enough to incorporate a spatial element, so EMICs and especially GCMs, divide the Earth into what we call either cells or voxels. So you're probably familiar with the idea of a pixel, right? You take a photo and you zoom way in on it and you see it's made up of all these little squares. Those are pixels. Or picture cells. So a voxel is a volume cell or a volume pixel. So it's a three-dimensional box. And so we divide up the atmosphere and the oceans and the land surface into these voxels. And each voxel will have a value for each variable that our model is measuring. So each voxel will have a temperature variable, for example. So what is the temperature of this chunk of air? That's what the model says for that voxel, and then it's different temperature for the one next to it, and different one for the next one over. The atmospheric pressure might be another variable that's assigned to each voxel. Wind speed and wind direction, CO2 content, right? All these different variables that we have are assigned. We have a value assigned to each voxel. And we can increase our spatial resolution by making those voxels smaller. So we have more voxels covering our area, so we can have more complexity, more differences in what we're seeing. We're not averaging together such a big chunk of land. And you can see how that complexity increases by looking at these 4 GCMs that were used in different reports put out by the IPCC, the Intergovernmental Panel on Climate Change. We're going to be talking about the IPCC and their reports in our next lesson. But these are summaries of the state of climate science at the time that the report was put out. And so the first assessment report, FAR, used GCMs that had voxels that were 500 kilometers to a side. And when you look at that, you can barely recognize what part of the Earth that is covering. And when you went to the second assessment report and they cut that in half, they started using voxels of 250 kilometers to a side. Third assessment report, they used voxels 180 kilometers to a side. The fourth assessment report, they used 110 kilometers to a side. And as you go through those, right, you can start to recognize the detail of Europe and the North Atlantic, which is what's in this particular diagram here, right? We're getting a lot more detail of what's going on spatially as we decrease the size of those voxels. The trade-off is that it's a lot more computationally intensive to run a model when it has more smaller voxels. So if you imagine going from that first assessment report to the second, where we cut the size of voxel sides in half. If you have one voxel and you cut it in half east to west, now you've got 2. You cut both of those in half north to south, now you've got 4. And you cut both of those in half up and down, right, because these are 3-dimensional things. Now you've got 8. So you've turned one voxel into 8 voxels. So that means it's going to take 8 times the computer power to run the model, because it's got 8 times as many voxels as the previous one did. And so that's why some of these GCMs require supercomputers to actually run this. You're not going to run one of these on your home laptop and just get some results. So you have to have a lot of computing power behind it and run these for quite a long time, because there's a lot of different variables that they're dealing with, and they're also very fine scale in terms of their temporal resolution as well. So we can build this model, and we can put all these variables into it, and we can create mathematical equations that tell us what should happen. If the temperature in this voxel is this many degrees right now, and the amount of CO2 is this much, how should it change by the next year or whatever, right? That's what the mathematical equations are describing. How should these variables change in reaction to other variables in that voxel and neighboring voxels? How do we know that what this model produces is real, is accurate, is telling us something worthwhile about our Earth? Well, one thing we can do to test the accuracy of models is what's called hindcasting. So hindcasting means we're going to check the accuracy of a model by giving it starting data from some point in the past and seeing if it can accurately predict the present. And we already know what we've got in the present, right? We have the actual information for that, and so then we can compare those and see, did the actual things that happen pretty well match what the model predicted would happen? And if they do, then it seems like the model has a pretty good idea of how these processes works and is giving us accurate information. Another thing to note about hindcasting and forecasting with models is that these models have a probabilistic element. There's an element of randomness in them. So we never just run the models once. Instead, we run the model a whole bunch of times. So that we're rolling the dice slightly differently in each model run, and then we take the average of all those runs. So we do a whole bunch of different model runs and then average them together and say that's the output from the model. So the image there is an example of some successful hindcasting. So what you're seeing there, all of the very thin little yellow lines are the predicted temperature anomalies over the course of the 20th century from a particular GCM. So we ran it a whole bunch of times and put those all on our graph here. Those are all the skinny little yellow lines. Then the red line is the average. So we took all of those model runs, we averaged them together and said that's the average output of this model. And then we can compare that to the real data. So the real data is the black line. And so what we can see there is that if we are feeding this model our starting conditions in 1900 and the changes that we knew happened over the course of the 20th century, then what the model tells us should happen with global temperature matches up pretty well to what actually happened with global temperature, right? Those two lines follow each other pretty closely. And this particular image I like because it highlights one of the ways that knowing the actual things that happened feeds into these models. So you've got those 4 names on there: Santa Maria, Agung, El Chichon, and Pinatubo. Those are notable volcanic eruptions. And volcanic eruptions have a short-term cooling effect on the Earth because all of the material that blasts out of a big volcanic eruption goes into the atmosphere and increases the Earth's albedo. So for a short period of time, a few years, we get this big boost to albedo, reflects away more sunlight, and has a temporary cooling effect on the Earth. And we can see that not only did the actual temperatures of the Earth temporarily drop after each of those big eruptions, but the model picked up on that as well. The model, knowing that there was an eruption, calculated that there would be a drop, and those drops are pretty on point. They pretty much match what actually happened in the world. So if we can successfully hindcast, if we can predict the present based on data from the past, that tells us our model is something we can have confidence in when we forecast, when we use present day conditions to predict what's going to happen in the future, because we can't double check the future against actual data yet. We have to wait until the future happens, but we want to be able to predict in advance. So if our model's good at hindcasting, we can trust that it's going to be reliable for forecasting the future. Now here's the catch about forecasting the future, is that human activity plays a big role in our climate, right? That's the whole reason we're worried about it here, is that what people do affects our climate. Our amount of CO2 that we put out, our things that we do that change land cover and therefore albedo, those all have an impact on climate. And when we're hindcasting, we already know what we did. We know how much CO2 human activity put out in each year over the course of the 20th century. So we can just plug that into the model. We know how much deforestation people did each year over the 20th century, so we can just plug that into the model. But if we're looking at the future, we don't yet know exactly what we're going to do. Right? We don't know for sure if, for example, people are going to very quickly change over from gas cars to electric cars and therefore drastically reduce that source of emissions, or if it's going to be a slow transition. And so there'll be still a lot of gas cars running for quite a while. Right? We don't know that for sure. We know exactly how many cars we drove in the past, but we don't know for sure what's going to happen in the future. And this is why I say in the sub-bullet point there that I believe that social science is harder than natural science. So natural science, you're dealing with natural processes that don't have the ability to make decisions and change their minds and so forth. And so it's much easier to predict what's going to happen to natural systems than it is to predict what's going to happen with social systems, with cultures and politics and economics and all those kind of things. But those kind of things affect our natural systems and are essential to being able to forecast with a model. So what we do is, rather than trying to make a single forecast, we construct a range of forecasts based on different things that people might choose to do. So it's an if we do X, then here's what happens to the climate. If we do Y, then this other thing happens with the climate. It's an if-then kind of thing. Each scenario, we can figure out what might happen to the climate under that scenario, and then that allows us to decide, do we want to try to imitate this scenario or that scenario based on its climate effects? So in order to forecast climate, we have to construct these scenarios about what people are going to do so that we can incorporate human activity into our model predictions. And there's two different ways that we can do this. They're called bottom up and top down. So if we're constructing a bottom up scenario, we start by kind of trying to tell a story about what people might do in the future, right? So we might tell one story where everybody starts taking climate change really seriously and makes big changes in our CO2 emissions. Then we might tell another story where people don't take climate change seriously or have vested interests in not doing something about it, and so we continue to do a lot of emissions, right? We tell these different stories about what might happen in the future. Then for each of these stories, we can estimate how much greenhouse gas emissions and how much albedo change that story would lead to, right? What would happen to these human-caused radiative forcings in that scenario? And then once we have those estimates of albedo change and greenhouse gas emissions, then we can convert those into the radiative forcings, the actual change in energy balance of the Earth. And then we can plug that into our models, and it'll tell us what will happen to our climate. So that's a bottom-up scenario where we start by trying to imagine what people might do, and then we build a scenario out of that. A top-down scenario, we start with the outcomes that we're interested in. So we take different sorts of radiative forcings that we're interested in seeing. What would happen if we had this radiative forcing? What would happen if we had that radiative forcing? And then we work backwards to say, okay, what might people do in terms of greenhouse gas emissions, for example, that would result in that level of radiative forcing? And then what would have created that amount of greenhouse gases, right? What kind of human activity would have led to that? So we're working backwards, starting with a radiative forcing that we're interested in exploring, backwards to say, what could people do that would bring about that scenario? And both of these types of scenarios are used in climate modeling, and you're going to encounter both of these kinds of scenarios in your activity for this week. So here's an example of some bottom-up scenarios that have been widely used. And so, you don't have to remember these scenarios and the names of them and what goes into them, but this is just to illustrate the kinds of things that are incorporated into building a bottom-up scenario. So if you'll notice, one factor that goes into these different scenarios is population, right? How many people do we have on our Earth? So the A1 scenario here says global population peaks in mid-century and declines thereafter. So sort of low population growth kind of scenario. A2 says continuously increasing global population. B1 says population same as A1. B2 says continuously increasing global population at a rate lower than A2. So we have different things that might happen in terms of global population that distinguish these scenarios. Then you'll see economic growth, right? Do we have a lot of economic growth? Do we have slow economic growth? We have changes in technology, right? Do we rapidly introduce new technologies that might make our energy production more efficient, for example, or are we slower to do that? Is there convergence between different parts of the world in their economies, or do they stay kind of regionally distinctive? These are all things that are going into these scenarios. So you put together these different kinds of features in kind of plausible packages, right? If we're thinking of a scenario where a global population peaks in mid-century, well, what kind of economic growth would likely go with that, right? And we build this package. And so here we've got these four packages, although the A1 is then also broken out into three sub-scenarios here. And from that, we figure out, well, if that's what people were doing, how much greenhouse gases would we emit? And then from that, calculate our radiative forcings. So here's an example of some top-down scenarios. And so whenever you see this RCP, that you're dealing with a top-down scenario. RCP stands for Representative Concentration Pathways. And then it's followed by a number. That number is the radiative forcing in 2100 that model or that scenario is aiming at. So RCP 8.5 is a scenario that will lead to 8.5 watts per meter squared of additional radiative forcing by the year 2100. RCP 6.0 is a scenario that will lead to 6 watts per meter squared of additional radiative forcing by the year 2100. Same thing, RCP 4.5, 2.6. So climate scientists picked out these levels of radiative forcings as ones that they were interested in. And then we worked backwards to say, okay, what kind of greenhouse gas emissions would lead us to that point where we have, say, 6 watts per meter squared of radiative forcing in 2100. And so the graph there is showing you the CO2 equivalent emissions that would happen over the course of the century that would get us to that endpoint of the scenario. Okay, so any of these RCP, some number, that's representative concentration pathways that lead to that number of watts per meter squared of radiative forcing by 2100. Okay, so we've got these different scenarios, and we can now plug them into our GCMs that have been validated through hindcasting and see what they tell us would happen in the future under these different scenarios. So our current GCMs, our best ones, predict our average temperature anomaly in 2100 will be somewhere between 1 and 4 degrees Celsius. So if you recall, we're getting close to that 1 already. Right, when you looked at our temperature anomalies of data we actually have, we're getting pretty close to that 1 already, and it could, not go much more. It could go all the way up to 4 degrees Celsius by 2100, depending on which of those scenarios turns out to be the real scenario of what people actually do. And it's increasingly looking that those lower emissions scenarios that therefore lead us to lower temperature anomalies are out of reach, that we are unlikely to be able to actually achieve that with our, political and economic constraints and so forth. So we're moving a little more towards some of the higher ones, but exactly which one we get depends on things like, do we all switch over from high emissions forms of energy like fossil fuel burning to lower emissions ones like wind and solar energy? Right, those kind of choices that people have to make are going to determine which of those futures is the one that actually comes about. Then I've also got, since we were talking about sea ice the other day, got some projections of sea level rise. And so again, depending on the scenario, we get different levels of sea level rise. And so that could be anywhere from 0.4 to 0.8 meters by 2100. So we could get, from a little less than half a meter to almost a full meter of sea level rise. And same deal with the temperatures. The lower ones are increasingly looking out of reach, increasingly unlikely we're actually going to follow that pathway in actual reality by 2100. Okay, so we can check our models by hindcasting. We can also check models as they go into the future by keeping an eye on the actual data. And so we can look at older models and see how well did they actually predict things. Should we have been taking those models seriously back when they came out, when they were forecasting things? Because did we actually experience the things that those models were telling us we were going to have? And what we find is, generally speaking, and there's a lot of climate models out there with a lot of different results sometimes, so this is a generalization, but generally speaking, most of our climate models, and especially our most respected climate models, the ones that have the largest kind of backing by climate scientists, have fairly well predicted actual temperatures and other aspects of climate change as we've gotten into the time periods that they were forecasting. So the diagram there shows one of the earliest really successful GCMs from a paper by Hansen et al. In 1988. So way back in 1988. They did some hindcasting and it seemed to match up. And so then they did some forecasting with this model. And so keep in mind, this is 1988. So this model is a lot less sophisticated than the ones that we have today. It's a lot less complex. It has a lot less spatial and temporal resolution because we just didn't have the computing power to run some of the models we have today. We didn't have some of the knowledge that we have today about the climate system. But based on what they knew back in 1988, they fed some different scenarios into this model, did some forecasts, and told us what they thought would happen by 2020. And so on this image here, you see the light green is their highest radiative forcings scenario, the one with the most human activity, most changes to climate. Then the red line is sort of their middle scenario, and the light blue is their lowest emissions scenario. And then the black line shows actual temperatures. Okay, so that's our actual what we've observed, because it's now past 2020, so we can look back on this like 3 decades worth of forecasts and see how accurate they got it. And we can see that we didn't warm as much as some of their higher emissions scenarios were predicting, but we were within the range of their lower emissions scenarios. So they were fairly good for, again, you're thinking of models that were put out 30 or 40 years ago. They got it fairly good. And luckily, we have not experienced the worst case scenario predictions that they have. And there are sort of a subset of models that tend to overestimate some of the temperature increases. This is a thing that climate scientists know about, are working on figuring out why, what is it with this subset of models that tend to overestimate things somewhat. Other models are like this pretty well spot on. So I think we can have a lot of confidence that our models are accurately telling us, if we do this, here's what's going to happen to our global temperature. If we do this, here's what's going to happen to global sea levels. If we do this, here's what's going to happen to snow and ice cover, all the different things that might be predicted by the model. So then that gives us a good basis for choosing, do we want to do this scenario? Right? Do we want our choices as individuals, as a society, to follow this scenario or that scenario? I think our models are giving us pretty good information to make an informed choice there. So for your lab activity for this week, you're going to be looking at some simple climate models. You're not going to be able to run a GCM on your computer, but we're going to be looking at some EMIC, some models that have a little bit of complexity to them, and using that to forecast the impacts of different policy choices on the Earth's climate.